Okay, so this is transformations of the complex plane. This is in fact part 2. In part 1 we talked about some very straightforward translations and enlargements of the complex plane. In this one we're going to do the proper stuff, so we're looking at some Möbius transformations. And one of the ones we mentioned right at the end of the last video was this one, W is equal to 1 over z plus I. This is a Möbius transformation. Now, I mentioned the word Möbius transformation because I never say it anyway. The book doesn't mention it. The exams won't say the words, so there's really no need to know about it. But hey, I'll say it, so you have to put up with me talking about that a little bit. And I think it is helpful. These kind of transformations are used by the book and used by the exam papers because they map straight lines to straight lines or to circles, and similarly map circles to straight lines or to circles. And because we've done a lot about loci of circles and straight lines over the years in both sort of normal maths and further maths, and even earlier in this chapter, they're quite nice. So they will use them for that reason, and maybe you'll see them in your future maths career if you do more maths at a higher level. Maybe you won't. Maybe you don't care. Anyway, this is the kind of question we're going to have to be able to answer. So let me write this down. So the kind of thing they'll ask you in exams like this: show that the real line in the z-plane, so that's a straight line, right, is mapped to a circle, which we'll call C, in the w-plane. And moreover, can you find the equation of this circle C? So the real line is the line here, the real axis. Try to make that bolder so you can see it nicely. What's special about the real line is that when you write z in terms of x and y, the x-axis is the axis, and so y is always 0. There's no imaginary part, it's only a real part. So this is what makes it special. We've got to show that somehow means we get a circle over here somewhere. To show that we've got the equation of C, we can either write it in terms of w, so like a loci, a complex loci type thing, or we could use the real and imaginary parts of w called u and v traditionally, and get a sort of Cartesian equation in terms of u and v. And it's actually the second thing that we'll do today, although there's no way of knowing that immediately unless you've done ones before. Why u and v? Well, just look at the last few letters of the alphabet and you'll see that those ones there give you z, and then those ones there give you w, so u is like x and v is like y. Mathematicians are sometimes helpful. So we've got to use this and this. It's the only things we have to find this equation of C. So we start with this, and we've got to sometimes use this information. Now, to use the information about y, we really need to be able to get it in the form of z equals, because then we can actually use the fact that we can separate it in terms of real and imaginary parts. So the first thing we do in these questions is rearrange for z, because we know a bit about z. So we do that by timesing by z plus I. We expand this out, wz and wi. We take the wi to the other side, and then we divide by w. What I'm doing is getting it in terms of z. That should be a w, is there? So we've got now z is equal to 1 minus wi over w. This is always possible with Möbius transformations. You always can rearrange for z. Sometimes you've got to get the z's to one side and factorise the z out, but you'll always be able to get it in terms of z. Why is that helpful? Well, it's helpful because if we rewrite the z as an x plus iy, if we can get this side, so it's a real part, an imaginary part, we can say x equals and y equals, and then we can use the fact we know y is equal to 0. So the whole push, the hardest part about this whole process is getting this thing now and manipulating it in some way so we get a real part and imaginary part. And the minute we haven't got that, because w is complex, it's got real and imaginary, and so the bottom is both real and imaginary, and while that's the case, nothing's going to work. So what we're going to do is we're going to rewrite it And the same way you change z to x plus iy, we're going to change w to be u plus iv. And then we're going to work out what the top is. So we're going to do minus I times u, so there we go. And we're going to do here I times I, which is minus 1, times another minus sign. So that's two minus signs, that's a plus sign, plus v, and that's over u plus iv. And that's going to give me, I'll just collect the real parts together, 1 plus v, and then the imaginary part there is u. But of course the bottom is still imaginary, and while that's the case, we haven't really got separate real and imaginary parts. So to get the bottom to be real, we're going to times it by its complex conjugate, something that you'll have done lots of times in FP1, times by the complex conjugate at the bottom. Of course, this is all algebraic, which just makes it look harder, but it's really not any more difficult than times by numbers. So we times by the complex conjugate. Let me just rewrite this at the top here so we can see what we're looking at. I'm just going to rewrite the top. I'm not going to try and do calculations because it'd be too easy to make a silly mistake when you're copying from the bottom page to top page. In fact, I might do the bottom though. The bottom would be alright because when you times a number by its complex conjugate, you know you get its modulus squared. Because you do u times u, which is u squared, and then here, minus I times I, well, I times I is minus 1, times another minus 1 is plus 1, so you've got two minus signs there, and then the v squared, and then all the other terms, because of the, difference of two squares, the in-between terms cancel each other out. So we're left with this. Now I'm just going to do the top, get it as a real part and imaginary part. So we'll times together this one by this one, so we get 1 plus v times u. And I'm going to times the last two terms together, so I've got u times v, and I've got two i's. So, I times I is a 1 minus 1. I've got another minus sign, and third minus sign, that's three minus signs, so it's going to be uv. The i's have gone away. That's my real part. My imaginary part will be these two middle terms times together, so minus u times u, which is minus u squared. The i's come out the front. And then these two end terms times together, so that's minus v times 1 plus v, and of course the I there has come out the front. See how I did that? I did the first two terms and the last two terms to give you the real parts, and then I did the in-between terms to give you the imaginary parts. I find that helpful rather than doing them in another order. You haven't got to, just giving you suggestions. That's still equal to x plus iy. Now the good news here is actually we've now separated this into real and imaginary parts, right? So this is the real part over u squared plus v squared, and this is the imaginary part over u squared plus v squared. So we can actually rewrite this as the real part here is equal to the real part here. And we can take the imaginary part and write that as equal to the imaginary part over here. And now we actually made some progress, believe it or not. The reason being, although we don't know much about x could be any number it likes because it's, it's the real axis. The y bit has to be equal to 0. So what we know is that this term here must be 0. And if you look at, forget the y now, look at this bit here. This actually is a Cartesian equation. It's in terms of u and v because we're looking at the w plane, so that's like x and y. But we've got an equation in terms of u and v. And this, if we manipulate it, we should be able to see a traditional circular equation if we work hard enough. So the first thing I'm going to do is take the bottom and times by it. And 0 times the bottom is going to be 0. So it's going to leave us a nice straightforward equation. And now we can expand this bit out. I suppose we can now times everything by minus 1 to get rid of the minus signs. I'm just going to rewrite this u squared as being v squared plus v is equal to 0. Now to show the equation of a circle, we need to complete the square. And of course we've got to take away the half squared. And then we just rewrite this. So we can see now the centre is 0 minus a half. And the radius is a half. So over here, this has been mapped to minus a half, radius of a half. And that's your circle C. Not easy, but doable, and it is very similar each time. So good luck guys, and I'll see you next time.